Hello, 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 hello. Can you hear me? Can you hear me? All right, Zoom is picking up. Hey guys, so this is just going to be a redo of that second hour of that EAS video. Apparently, it turns out if you leave your computer running with Zoom open and you mute yourself, Zoom decides after like 5 minutes or however long, because I had gone to the gym after, it decided it's not going to pick up on audio anymore, even if you record again, which is really frustrating. So I actually have zero audio for that second part. I thought maybe it was just an audio, like it picked up the audio, it just didn't like put in the video, or whatever, but it didn't. So we're just gonna go ahead and redo this second half, which is okay. I think it clocked in about an hour, so we'll do about the same. This also gives me the opportunity to kind of also address some things I'm noticing in the Discord in terms of like the common questions, particularly the first common question. Actually, you know what? Let's actually just, since we're even just talking about this, it might even just be helpful to just go over very quickly again what we learned in the first half. Very, very quickly. So we talked about how there is a two type of mechanisms, right? The H2SO4 dehydrations, which I will just annotate as minus H2O. And then we have the 3 Lewis acid reactions, right? So I'll just put here LA, like that, the Lewis acid reactions. And so these look like SO3, H2SO4, which installs an SO3 group, SO3H, sorry. And then NO2 if you do HNO3, H2SO4. Okay. So again, one common question is, how much of the mechanism we need to know. Again, there is the common mechanism we see with every single EAS, which is you attack that super electrophile. You do the resonance forms, and then you just eliminate out that hydrogen on the same carbon as the electrophile, and you get back your benzene ring just with the electrophile on it. So that's something everyone should know. I mean, I think this should be in your primary brain. This doesn't really belong in a note card. You can put on your note card if you want to, but I think having this in your brain understood is just really going to be helpful and will, give you a good idea as to what your product should always look like. Right? It's a benzene ring with some electrophile on it. And then the other part of the mechanism is always just going to be how we make the electrophile, which again can differ, but at least on, in our categories on the left side, it's just pulling out water, right? So if I want to make the SO3, electrophile, I just turn this into water and it falls off, right? If I want to make the NO2 electrophile or the HNO3 electrophile, right? I'm just making water and I'm just kicking it off, right? So that's kind of the point of breaking this up into categories, is to help you guys, recognize the patterns so that you can quickly get through to the products. With the upcoming carbonyl section, right, that's going to be incredibly important. Incredibly important. I mean, this is just 5 reactions, right? Which let me just, as I'm talking, I'll fill these in, but this is just 5 reactions, right? When we get into carbonyls, you guys are going to learn a lot of reactions and you're going to feel really overwhelmed, which is okay. I'm not trying to say that it's not okay to feel overwhelmed, but you will feel less overwhelmed if you start to recognize patterns and start to see how certain things are adding, so that you can quickly predict what's going to happen. And you can start to group things together as, oh, these have similar types of reactions, so these will do similar types of things. So I don't have to remember like 20 mechanisms. I only have to remember like 5 of them, because five of the 20 and every, 5 out of 20, 5 out of 20, 5 out of 20, 5 out of 20, whatever, they all fit into, 4 types of mechanisms or something like that. Okay. So very, very important that you guys start building the skill. I mean, this is just really well, translating over to, oops, sorry, not that. This will just help really well translating over to other aspects of life as well, and other classes as well, where there's gonna be a lot of information. So you got to learn how to segment it. Okay. So these are our Lewis acid mechanisms, right? The number one thing everyone's having a hard time with is the Friedel-Crafts alkylation. I totally understand that's a difficult one. Just keep in mind the general rule of thumb, right? When it comes to those reactions, right? If you ever have some kind of alkyl chain that's longer than 2 carbons, okay? So that's kind of the requirement. Is it just longer than 2 carbons? Keep in mind that it's always going to rearrange to that next door carbon, right? So when we get the metal here, we get that hydride shift, right? The hydride shifts over, X falls off, we get that cation there. So always when you see a carbon chain longer than 2 carbons, or primary halide longer than 2C, right? You should definitely expect it to rearrange, right? Because if we didn't, right, we make that cation that looks like this. So let's say we didn't rearrange, we just let the X fall off. We make this cation here. This is a primary carbocation, which is, as I've been saying quite a bit, it's primary cringe. Okay, please don't draw it. This is primary cringe. Don't draw it. So anyways, if you need to figure out, or if you need help figuring out, or you need some kind of method that'll help you figure this out, you can always just draw the cation. There's no, it's not like you're not allowed to do it. But you can always draw the cation, and if it's primary, just put it on the next door carbon, right? Just rearrange it. There you go, right? You're like, oh no, I made the primary cringe. That's okay, I'll move it to secondary, right? Let's say you do this, but what you get is a secondary cation. So let's say maybe the chlorine was actually on that secondary carbon. Hey, guess what? Secondary is okay, so it's just going to stay there. It's fine. It's not going to rearrange. It'll stay there. Okay, so if you need that trick, you can go ahead and use it. Whatever you got to do, right? Just remember, no primary cations. So if you have a primary halide longer than 2, we should expect a rearrangement. But in every other instance, right, like let's say I have this chloride here, right, that's just going to form the, tertiary cation, and benzene is just going to add to that cation, right? Cool. All right. So that's just what I wanted to, I guess it's great that the audio went out because now I get to emphasize this, which is, I'm okay with that. But yeah. So with that being said, let's get back into the main question of this second part, which is, I have been doing reactions where I add an electrophile to a naked benzene, right? So a benzene with nothing. But what happens when I add another electrophile, right? What is going to determine where this electrophile is going to go? Technically it could go to 5 different spots, right? 1, 2, 3, 4, 5. Although I guess really it's 3. Right, because it's like these are the 3 unique spots. The other 2 are just like symmetric of the other, whatever. Anyway, so those are the 3 places I could go, right? And so we actually have names for these, which I'll just kind of put here. Ortho is right next door, meta's 1 over, para is right across. Okay, so I have these 3 positions where things could go, right? What determines that, right? Is it just, do I just guess? Is it always just going to be a mixture? Will I always get one here and then I'll get one here and then, one opposite? Is that what's going to happen? Is it always just a steric based, like, oh, it's just steric, so let me just put it here, right? What is going to determine where things go? Well, this is where we're going to cover the directing effects of the original electrophile that you added on. So what kind of group you have on benzene actually will determine whether benzene has electrons or doesn't have electrons, and that can determine where things will go around the ring. Okay, and so the first type of director is what we call the activator. Okay, so we have what we call activators. So what is an activator? Well, an activator is usually some atom with a lone pair. So this is the key characteristic of the activator. It is some atom with a lone pair next to the ring. Okay, so why is that lone pair important? Remember, electrons, if they have the ability to, want to resonate with the benzene ring, or with any type of polyene, right? But in particular, right, if I have a pi bond next to a lone pair, that lone pair really, really, really wants to resonate. Okay, so if this atom has a lone pair, it will definitely give it to the ring. And as you'll notice, right, now we have a net negative inside the benzene ring. Sorry, I'm trying to be consistent with things, but my brain is a little floppy right now. Okay. All right. And then there's one more. I'm just going to quickly draw this, and then I'm going to erase it just for the sake of space, because I just want you guys to notice that the negative charge, when I move it once more, right, it actually lands up in what is technically an identical position, in the sense that, it's right next door to A, just like it was in the first one, just like that. So, oh, oops, like this. Sorry. So these two are essentially identical in the sense that they're in the same location relative to A. So I just want to show it, but I'm just going to go ahead and erase it just for the sake of space. But we have now extra electrons in the ring. Okay, so first thing first, right? The most obvious thing is that an activator, an atom with the lone pair, adds electrons to the benzene ring. Okay, so benzene gets more electrons. Well, hey, guess what? Right? If benzene gets more electrons, that makes it more nucleophilic, right? Because the whole point of being a nucleophile is that you have electrons. So if you have an excess of them, if you're gaining electrons, you're going to be even more nucleophilic and be more powerful, right? As a electron donor. And if it's more nucleophilic, remember these are electrophilic aromatic substitutions, right? Where we add electrophiles to the benzene ring. So if I'm adding an electrophile, I'm saying, hey, I'm giving my benzene ring more electrons, making it more nucleophilic. And at the end, I'm going to add an electrophile. Guess what? That also means that the reactions are going to go faster. Because if you have a more nucleophilic ring, right, and the ring is the nucleophile, then of course the reaction is better. Higher yield. The reason for this is just sterics, right? Which is kind of interesting, right? Because technically there's two ortho positions, right? So you would think, oh, two ortho positions versus one para position, there should be more ortho. But now you can see sterics is a huge thing. So sterics is a very, very big thing. Sterics plays a huge part, especially on benzene rings where everything is flat. Everything's kind of forced to be in the same plane, right? It's not like A and E can kind of go out of plane. Like if this were a normal cyclohexane, A could be a wedge and E will be a dash, and they'll be away from each other forever, right? They can just be axial and be away from each other forever, right? But because everything is flat and planar in the benzene ring, they have to talk to each other. They have to, they have to be next to each other. Okay. So usually you'll see a 40-60 split. The nature of A can make it so that there are, different levels of sterics, right? For example, it's different to have an NH2 versus an N with a carbonyl, right? The N with the carbonyl is larger, so it can have a bit of a more steric effect than the NH2 without it. But I believe in this class, you're just always going to assume if it's orthopara, draw both. There are two exceptions, which I can show you guys. But it also has, it also reminds me that I have to include one more activator group. Okay. So again, we have two types of two main characters in the activators, right? The N and the O groups. We also have carbon chains. So you can imagine like a CH3, right? Or like an ethyl or a propyl, isopropyl, or actually, I guess that's actually a isobutyl, not an isopropyl. Isopropyl would have been this. That's would have been isopropyl. This here is isobutyl. Anyways, any carbon chain, right? This is also going to be a donator. Now you might be looking at me like, oh my God, dude, you just said we need a lone pair. And that is true, right? If you have a lone pair, you do have the ability to donate via resonance. So these guys are resonance donators, right? Because they have the lone pair to give in, right? And these guys are typically very strong, right? They're a lot stronger than this guy here, because again, CH3 doesn't have a lone pair. So what is it about CH3 that allows it to donate? Well, if we just think about CH3, it's an sp3 carbon, right? sp3 carbon, let's just add it onto here really just for the second. sp3 carbon bound to an sp2 carbon. sp2 is more electronegative. So we do have a slight induction from the sp3 carbon to the sp2 carbon. And that slight induction, that slight donation is all we need to get a bit of an activation effect. Okay. So this here would actually be an inductive donator. Fun fact, carbon groups are the only inductive donators in this unit. So if you ever have a question about which one of these guys are an inductive donator, or you're asked what kind of group is a carbon group on a benzene, it is solely inductive donating. It is unique to that group. Okay. Now induction effects, again, they're just through bond. They're not like through pi bond, they're through sigma bond. So the effect's not the strongest, but it is still measurable, right? That's why we also see that a thing in Friedel-Crafts, which I'll bring up in a second. Okay. Now, on that fact of induction, right? Nitrogen and oxygen are also very electronegative. I mean, if you guys, you might not know this, but there's a little acronym, Fonkel-Bursch, which you can use to navigate electronegativities, relative electronegativities of particular atoms of interest. And you can see right on the top here, FON, right? O and N, those guys are the most electronegative, right? Compared to everything else. So you might think, well, wait a minute, shouldn't there be an inductive effect, right? Coming off of these heteroatoms? And that is true. Every single heteroatom we're going to see in this unit. So when we see F, when we see O, N, Cl, Br, and even I, and when we'll talk about S, but S also has this too, right? There's always going to be some level of inductive withdrawal. Okay, there is going to be some inductive effect from these atoms, especially from N and O. Okay. Oh, not, let me put withdrawal here. Which might be a little bit interesting because you might think, oh, wait a minute, if these guys are real electronegative, why do they want to donate? Turns out that these two effects on heteroatoms are always clashing. They're always fighting. They're always, they always want to turn. And in the case of N and O, right, the resonance donation is just stronger. This is just a stronger effect. So both effects are present, right? They're always constantly fighting each other, but the resonance donators, I mean, they drank more milk. They drank more milk, right? Their bones are stronger. These guys are gonna, that effect is just a lot more prominent. Okay. It also has to do with the fact that N and O, when you consider their orbital overlap with the carbon. So for example, if we consider the orbitals that allow them to resonate, they are the same row. So because of that, the overlap is insanely good. And so that donation is it's just so much better to donate electrons, like provide stability for those electrons via resonance than it is just to, inductively pull out electrons. So heteroatoms, as we're going to talk about, they all have some level of inductive withdrawal. It just turns out that when it's nitrogen and oxygen with a lone pair, those guys are just going to be way powerful. So let's go through synthesis here, right? You're very likely to start from a benzene ring and ask to do 2-3 possible transformations on it. One popular one could be this one here. Add an NO2, and then maybe to this NO2, what you can do is H2PD. Now, I can't remember if I talked about this in the last one. I know I talked about this in terms of the ketone. So I know I talked about it if you did like a Friedel-Crafts alkylation, or sorry, acylation. Right, if you do H2PD, this reduces out the ketone. Right, turns it into an R group. And so that's how you make the non-branching center, right? This is how you make that center that's primary on the benzene. For NO2, what this reduction does is it turns the O's into H's. So it makes it an NH2. So I can't remember if I talked about that, but I saw this somewhere and I decided, you know what, it doesn't hurt to bring it up. But in both these cases, right, I mean, these are both, I mean, either you have the lone pair donation, so that makes this an ortho-para director, or you have the inductive donation, which also just makes this ortho-para director. So let's just say I added an electrophile like Br2, FeBr3, right? In this case, we'll just add Cl2, AlCl3, just to be a little different, right? We should expect, hey, 2 products in this case. Now again, one will be a lot higher in ratio, in distribution, right? I mean, we should expect that the para product. Oh, sorry. I just realized. Let me make it so that it looks like how I had it. So I'll put this here. Okay, there we go. That way it looks like how I had it the whole time. Okay, so we should expect some sort of like 60-40 type split here, right, between the para and the ortho, where para is higher. But again, I'm pretty sure you guys are expected to always include both, unless you were told about some very steric group, which again, I can show you guys an example of that. But this is a good synthesis that shows you that effect, right? Where all we're doing is we're saying we added an ortho-para director, so something should go ortho and para to it, right? The next electrophile will always go ortho and para to it, right? Another good example. Right. Let's just say we did a Friedel-Crafts alkylation, but now we make this tert-butyl group. Okay. Again, the active electrophile here, we don't get a rearrangement. We just get this here, right? That's what's going to add. So we get that branching center, right? That branching center, which alkylations are really good at making. And now let's go ahead and add an electrophile here. H2SO4, HNO3. Now you could add the NO2 to both carbons. Or sorry, let me put it this way. You could have 2 products where you add it to either of the 2 carbons. But this is where things get a little interesting, right? I mentioned that steric effects are very, very prominent because everything is flat on the benzene ring. So everything's forced to be in plane. Turns out when you have something as big as a tert-butyl, right? Tert-butyl is a very good para director. That is to say that you're going to get 80%, right, to 20% in terms of para to ortho. So the major product of this reaction is always going to be this guy here. Okay. So again, normally everything is about 40-60, 40-60, 40-60, right? Or 65-35 is another value you'll see thrown around too. I just did 60-40 so that it's a bit more, benefit of the doubt. But something like this is, where we have a tert-butyl, you're definitely going to have huge, huge, huge steric effects here. Very, very huge, because that tert-butyl group is huge. That's massive, right? And so what you're going to get is an 80-20 split, where this is the major. So what would I do if I were you guys on the exam or on the quiz and you get a terbutyl and you're like, oh, you know, maybe she never talked about this, right? If she did, then we can skip this part. But let's say she never talked about this, but she had this here. I would draw both and just label major minor, right? That way you can say, you know, you did draw both of them and you were also clever enough to think about, hey, you know, there is that steric effect on the terbutyl with the NO2. Now, I am aware of this being kind of a thing in the isopropyl. So maybe if there's isopropyl, you might want to do that too. If there's any more office hours with her, I'm not sure when your quiz is, but if there's any more office hours with her, it might be useful to just ask her this question too. But I know for a fact that terbutyl, I mean, everyone knows for a fact terbutyl is bulky. So that's going to be the case there. I would say for the isobutyl, sorry, for the isopropyl, so this example here, just draw both. But for the terbutyl, you can get away with drawing one and say it's major. Okay, cool. Now, there is another group like this as well, but instead of being from the director side, it's from the electrophile side. Okay, so we have just one more to go over, and then we can move on. Let me just, you know, there's actually no real way for you guys to add OR groups from scratch. So I'll just have to start from one. But we could add an OR group here. And let's say that we added an H2SO4, SO3. Again, very, very common and totally acceptable thought for you guys to think that these are the two products, okay? But if I draw out sulfur, right, if I draw out this sulfonate, hey, wait a minute, that shape looks really recognizable. That looks like three things coming out of a single atom. Gee, I wonder where I just saw that shape. Oh, huh. The terbutyl, where I had three things coming out of it, we determined was way too steric to be next to something, right? We determined this was way too steric. And it turns out in the sulfonate example as well, right, that is also going to be the case. So we can also have directors, so orthopara directors like terbutyl that only like to add things para, right? This is only happy when things are para. And we can also have electrophiles that only like to be added para, okay? So whenever you have an orthopara director and you're doing a sulfonation, the major product, again, like 85% is going to be this here, only about 15%. I'm not even 15 because actually this is how insane this effect is, right? You'll actually form more of this than you will of the, oh, sorry, haha, my bad. This is major. This is what's 85%, and this is what's 15, right? I mean, to say this is 15 is just to fill in the hole, right, from 18 to 15. Really, this is such a huge effect, this steric component, that this will form more often, despite not having the directing effect for it. So the meta product will form more than this product here will. So that, to me, I mean, that's kind of insane to me, right? Hopefully it's insane to you guys too. But anyways, yeah, this would be the major product. This would be the minor product. Very powerful industry reaction, this one. We actually, because of this, we call sulfur groups para blockers, because in synthesis, what you can do, right, how can we take advantage of this in a synthesis? So to put you guys in my shoes, right? Let's say that I have this here, and I have to make only, so I want to make only this product here. Actually, let's even make it worse, right? Let's say that I have this here, and I can only make this product here. Again, we just talked about how if I have a terbutyl, that's way too bulky, right? If I add NO2 straight up, so if I add the NO2 electrophile straight up, it's always going to go para, right? It's always going to go para. So how can I get product that's solely NO2 on the ortho position? Well, if I add an electrophile that only goes para, like SO3H, right? And then I add an NO2, so that I get NO2 here. Remember, from our previous video, SO3 is a reversible reaction. You can actually pull SO3 off. You just do H plus H2O, right? So actually, let me put it in a context that makes sense, right? Instead of having SO3, you have H2O, and that will pull off the sulfur. It's as if it wasn't even there to begin with. So again, maybe you don't need to worry about this for your quiz, but I thought it'd be cool just to mention, right? How you can use the bulkiness of a substrate to your advantage. Okay, cool. So orthopara direction, right? look for those lone pairs, right? The lone pairs are going to navigate you towards something that is a good activator. Oh, I guess I should have mentioned nitrogen's a better is better than oxygen, simply because the inductive effect is weaker on nitrogen. So its donation effect is better and its inductive effect is weaker, right? Oxygen's more electronegative. Remember Fonkel-Birch, right? O comes first. So that's that. Okay. So don't be afraid if you see something with a bunch of crap on it. If you see an atom with a lone pair right next to the ring, I'm guessing that it's an orthopair director. That's my instinct, and that should be your instinct too. Okay. And then just keep in mind that if it's just a carbon chain, right? Again, carbon chain with no functionality, so like something like that, or something like that. Any type of carbon, just carbon alkyl chain with nothing on it, right? Maybe even just like another ring. Just assume it's some kind of inductive activator. Okay, cool. All right, so that's the activating groups. That's what those guys are going to do. We also have deactivating groups, which you can imagine kind of do all the things opposite. Okay, they're going to do everything different, right? If these guys were not deactivating, or if I didn't have to make a case about them, if they were not the opposite, then we wouldn't be talking about them. We would just call it a day on the orthopara, right? But we can have some group with an atom A where A has some cationic character to it. So it can be a explicit positive, so it can be explicitly positive, or it can be a delta positive. So I'll put delta positive for now, because that's the weaker of the two, and that's the point, is that as long as it's delta positive, this will work. But if something is delta positive, right, it's going to want to take electrons. So we take electrons from the benzene ring. Oops, wrong arrow. And what we'll notice is now, instead of having a negative charge like we did earlier in the ring, now we have a positive charge. Again, I will show this resonance form here, but there's no real difference from the first one, right? Because at the moment, right, they're identical. These positions are identical at the moment. So I'm just going to go ahead and show it, but I'm just going to erase it because we don't necessarily need it. It's not showing anything that we don't already know. Okay. Now let me just actually let me do what I did last time, where I kind of made this also red. I like that. And then like that. Oops, sorry. Let me look at this page real quick so I can remember what I talked about. Okay. So I want it to be congruent. That's why I'm looking. I want these pages to look the same. Okay. But we are taking electrons from benzene. Right? That's why there's a positive charge in the ring. Right? We're taking electrons from benzene. So we're making it less nucleophilic. And again, if we're making it less nucleophilic, then the reaction is slower. It's worse. Right? This is now a worse nucleophile. Right? Again, the whole point is that benzene, these are hEArS reactions, right? Benzene is the nucleophile. So if you take away the one thing that is giving it the juice to react, right? You're taking away its fuel. Then there's absolutely no way that benzene wants to do a reaction, right? It's going to be a lot slower. These are usually very, very hard to do. Very, very trying, very, very toxic environments. I mean, if obviously at your guys' level, it doesn't make much sense. But if you were to look at some of the conditions that they put these guys through, oh my God, they're really intense just to get some of these products. Okay. Now there's a lot of groups that are like this, so it can get a bit overwhelming very quickly. But really, again, what we're looking for is the key element, right? Which is the atom with the positive charge. Okay. And so here are a couple that I think you should just know. And I'll even draw them out. These two you guys should know, because you know how to make these on a ring, right? You know how to add these two groups, the sulfonic acid group and the NO2 group, the nitro group. Okay. But here are a couple you should just be aware of. Okay, so the nitrile group, this is nitrile. This here is a carbonyl group. R can really be anything. It could also even just be another hydrogen, right? Which is, this is an aldehyde. This would be a ketone. R could even be like a heteroatom, right? Imagine if it has a lone pair, right? It's actually a great question. Do we even care that this atom has a lone pair, right? If the benzene ring is here, so let's say the benzene is here, do we care that this heteroatom here with a lone pair is there? No, right? It's not next to the ring. What's next to the ring is this carbon. So that's the carbon that dictates exactly what's going to happen to that ring in terms of electron density, right? Is it being added in or is it being taken out? Okay. But R can be a lot of things. It can be a heteroatom. It can be hydrogen. It can be carbon chain, right? So these are the main groups. I'll add in one more, CF3, which again, let me just draw this out. Okay. And so let's talk about these guys in terms of their effects. So again, these guys are withdrawing groups. And you can see some of these have heteroatoms in them, right? So we have an N, we have an S, we see an N, we see an O, we see Fs, right? So all of these are going to be to some extent, or not really to some extent, to a very, very big extent, these are all inductive withdrawing, okay? All of these, for certain, are inductive withdrawing, right? That shouldn't be too hard to see. Right. I mean, there's a positive there. I think I'm pretty sure I mentioned, if I didn't, I'll mention it now. The SO bond, again, SO bond, that is a minus positive bond or single bond where the S is positive and the O is minus. This is basically an S3 minus right here. Or sorry, S3 plus is what I meant to say. This is essentially an S3 plus, right? Insanely polarized, this sulfur, insanely positive. So definitely there's a dipole there. Carbon is triple bonded to nitrogen, right? So we shouldn't have a hard time seeing that dipole. So by all means, this carbon is going to be positive, right? So that's definitely positive, right? This is positive. That's for sure positive. We see it right there. Carbonyls, right? Double bonded to O's. We can definitely see that there. So we can see sort of how it could, as a whole, be a withdrawing group. So that's going to be positive. And then CF3, we have, remember, Fonkelburst, the first letter, F, right? That's the F in Fonkelburst. So of course, right, these guys are all going to be pulling on carbon, right, causing insane dipole, right? This carbon is definitely positive. So every single one of our withdrawing groups, right, every single one of our deactivating groups are definitely going to be inductively withdrawing, okay? But what's important to recognize is which ones are also resonance withdrawing, right? Remember, these guys don't have lone pairs to give. They take electrons. So if you want to take electrons, you've got to have some kind of p orbital, some kind of pi bond going on. In this first row up here, I mean, this was done strategically, right? So that the first row up here all has pi bonds. These guys have pi bonds. So these guys can do pi resonance. So these guys are also resonance withdrawing. So we can see a pi bond on this atom, a pi bond on this atom. We can see a pi bond, two of them on this atom, and see a pi bond on this atom. For sure, we know these guys are resonance withdrawing, right? The atom next to that ring has a pi bond, right? CF3 though, no pi bond, it's sp3, right? Same thing if this were like an nr3 plus, right? This one also gets people quite a bit because they see the the N with the, you see nitrogen, they think there should be a lone pair, but nr3 plus, that's a positive charge, right? So it's cationic, heteroatomic, so it has the dipole, right? And then on top of that, right, no pi bond, so it's only going to be inductively active. Okay, so these are only inductive. Okay, so you need that pi bond for resonance. Okay, cool. So where do these groups go? Where does A go, or sorry, E go when we add A? Well, if our ortho and para positions are positive, obviously the electrophile that's also positive is not going to go there. It's only one location. It's got to go meta. So inductive or resonance withdrawing, right? As long as these guys are withdrawing deactivating groups, these guys will also be meta directors. Okay, these are our meta directors. Okay. Now, one last thing for these meta directors, and specifically for the meta directors, it's going to make sense in a little bit why I'm, making such a big deal about it being meta. Okay, If a group is deactivating and it's meta directing, they will not accept Friedel-Crafts electrophiles. Okay. So if you want to do a Friedel-Crafts, it's got to be on a ring that's orthopara. So let's actually go back here real quick and say that these guys, orthopara directors, will accept Friedel-Crafts electrophiles. Okay, they will accept Friedel-Crafts electrophiles. Okay, so we'll go ahead and I'll make sure to put an example of this on the next page so you can see what you have to see to know it's not going to work. Okay, cool. So let's just go ahead and let's do a couple of these reactions, right? Let's just go with it. Let's say that I add in HNO3, H2SO4. Okay, and this is just going to add NO2 to any carbon on this ring. Now that I have a director on this ring, a meta director, the next electrophile that I add always going to go meta. Now there's two meta positions here. There's there's this one and this one. Again, at the time being, they're both the same. So who cares? Just put them on any of them, right? So you could have put on the other one. Whole point is that there's only going to be one product. It's only going to be this one. Okay. Maybe what I do here is I add H2SO4, SO3, and add a sulfur group. Right. Again, that's going to go meta. Now, there's definitely going to be someone that sees this and thinks, wait, didn't you just a second ago say that SO3 likes to go para? And that is true. SO3 likes to go para if the group is orthopara directing, right? So if this were, instead of NO2, this were NH2, then yes, you would be right. This would go here because that is an orthopara director, right? That's the whole point. But because we have NO2 that's meta directing, it's never going to direct para in the first place. We can't get the SO3 there. Okay, so we can have this here. Now let's say that I try to do this reaction here, right, where I add this here, and then I do that acidic workup. Right? How do we feel about this one? Right? I bet a couple people think that this is probably the answer, right? Hopefully some of you are like, whoa, 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 whoa. Why are you drawing that? Didn't you just say something on the other page? And you're right, I did say something. I said that meta directors will not accept Friedel-Crafts electrophiles. So in fact, actually, this is not going to form at all. This is NR. Okay. The reason for this is because Friedel-Crafts electrophiles are just carbocations, and those are not typically strong enough to motivate deactivated rings to attack. You need like severely positive things to do this, right? I mean, if we go back here, like a sulfur with 3 cation, with a 3+ cation character, right? That's a great electrophile. So SO3+, that's a great electrophile. NO2+, sorry, SO3H+ is what it should be. NO2+, great electrophile. Br+, great electrophile. These guys hit the mark for what is a very strong electrophile and will motivate even the least activated rings, the most deactivated rings, to go ahead and attack. But a carbocation is just doesn't cut it. It's not strong enough to do it. Okay, so Friedel-Crafts is not going to work. Now we can still make this. That's not, I mean, it's not impossible to make this, right? We just have to switch our strategy, right? If the whole point is that I cannot add in an electrophile to a meta, sorry, I cannot add in a Friedel-Crafts electrophile to a meta directing ring, then just add the Friedel-Crafts first. So this is usually the strategy in synthesis if you have to add a Friedel-Crafts electrophile. I'm just going to annotate for now. Actually, no, I shouldn't. So I'll just write it out. But you can go ahead and add this in, and then afterwards just add in your meta director, right? Because HNO3 doesn't have any limitations, right? Add your thing that's limited first. The thing that has a limitation, add it first, and then add the things that don't have limitations, right? So we can still make this ring. These two are the same, right? These two here are the same. So I'm gonna put it here because I don't have space on my screen to write down there. These two are the same. It's just flipped over. We just have to take a different strategy to get there. Okay. Now here's a cool thing. Actually, let's actually take this product real quick. I'm just gonna, I mean, this doesn't work obviously, but I just want to have it on the side here. Something cool that you can do with this, right? Remember we have that hydrogenation reaction, H2PD. So look at that. The end product is going to be an alkyl chain and a amine and an amine, right? Something with a lone pair and a carbon chain, right? These two should be donating groups. They should direct each other orthopara, and yet they're meta to each other. So usually in 118, 128, the question that you get asked is how you synthesize this here. And usually for some students, they look at this and they're like, wait a minute, who do I even add first? Because if I add the alkyl chain first, right, like that, if I add in an alkylation unit, that's going to direct orthopara. If I add in an NH2, right, that's going to be orthopara. So how do I do it? I like to call these chemical chameleons, right? These functional groups here are chemical chameleons because you can add them onto the ring as acylations and as nitrations, which are meta directors, get that meta relationship, and then change their functionality with one move, right? You've destroyed, or not destroyed, but you've kind of, created this electron paradox, right? Where two things that should not be oriented to each other a certain way are oriented that way. You can also think about this in terms of, like, let's say I did this reaction here, right? And then I did a chemical chameleon in the opposite direction. Right, so let's say I reoxidized and I re-added this in. You'd have to actually do this in 2 steps because I'm not sure you can do this in 1. For the ketone, you'd have to use some kind of chromic reagent, something usually very mild, like CrO3 in acetic acid, a very mild, and then you'd have to use like MCPBA for the second one. So obviously, I mean, you guys don't need to know this. So you can erase this from your brain. I'm just showing it to you. Again, we have this interesting sort of chameleon thing going on, right? I mean, we have these two guys masquerading. Why are they orthopair to each other when they're meta directors, right? There's no way you added them on, there's no way they were added on that way, right? There must have been some kind of trickery going on. So that's that there. I mentioned this in the previous video. Maybe you do need to know this. Again, I just want to make sure you guys know everything you need to know. I mentioned that if you have like an alkyl chain and you want to turn it back into its ketone, right? You can do the CrO3CH3COH, right? That's okay. This is a very mild oxidation, right? You can actually do even like a hyper oxidation if you use chromic acid, like straight up just very strong aqueous chromic acid. What that will do is it'll destroy the entire chain, right, and turn it into a carboxylic acid. The only stipulation, the only thing required for this though, is that you have to have these benzylic hydrogens. You have to have one of them. You only need one. As long as one of these guys exists, you can do this reaction here. Okay. So a very good question usually for this kind of reaction, if you need to know it. If you don't, just skip this part. I just want to make sure you guys are totally prepared for whenever your quiz is. So usually a question you'll get is something like this, at least on the 118 level or the 128 level. Right, so you get that super strong reducing agent. As long as that benzylic hydrogen exists, you can do it. So this hydrogen exists because it's right next to the benzene ring. This one exists, it's right next to the benzene ring, but this one doesn't have it. So the first 2 groups will be completely oxidized, they'll be completely substituted. Well, that's not really substitution. It's not really a substitution, but it looks like one. It looks like you're basically just switching it, right? That's a way to think about it. This one stays the same because it didn't have the hydrogen there. Okay, so just in case you need to know that, I'll just have it on there. If not, hopefully when I said it earlier, you just skip through it. I just want you guys to be prepared. Okay, cool. All right. So those are our deactivators. Now, there is a hierarchy on these guys. It's usually very confusing and hard to, to just look at them and be able to tell. I will tell you this, though. The number one absolute, if you see it, it is the best deactivator, number one deactivator, right? Number one hater, just like me. This is the gym functional group. It's the NO2. Okay. NO2 group, very, very powerful deactivator, the most powerful deactivator. Okay. Usually following that up is like CF3, but I don't know if you need to know that. So I would just know that this is number one. If there's, Dr. Levens is a pretty good professor in the sense that she will give you all the information you need. If there's any hierarchy you see in your notes, I would write that down on your note card. That is a very good thing to know. And you can expect on your quiz to be tested on that, right? Because she gave you that knowledge and she's also giving you a note card. So why would you not put that down? So default to your notes on this. Okay, cool. So before we move on, there's one last group that we have to consider, and that's the halogens. Okay. So why is it that I'm doing the halogens separately? Because these guys are a bit weird. They're electronic quagmires. Let's say I have a halogen. Okay. Halogens are interesting. Again, if we look on Fonkel-Birch, they kind of rank a bit high. Not really. I mean, in terms of the top three, right? After the top three are these guys here, are our halides, but they're definitely more electronegative than carbon. So to some extent, we do expect there to be a withdrawal effect, right? So we do expect it to be inductive withdrawal, right, on the halogen. But they also have these lone pairs. They also have these lone pairs, right? Kind of interesting. Okay. Now, actually, I almost forgot. F is actually the most. So F is all the way up here. So F is the most electronegative, right? So its inductive effect must be crazy. Okay. So the question becomes, right, what matters more? We asked the same question with oxygen and nitrogen. We said if oxygen and nitrogen were electronegative, but they could also donate, right? Which effect wins more? Okay. And that's the same thing with the halides, right? If F is here, right? F is super electronegative. So should it just completely deactivate the ring, prevent anything from happening, right? Is its electron lone pair donation not that significant, right? What about an iodide, right? Iodide is huge. So I mentioned that thing about that carbon and nitrogen and oxygen being in the same row, right? Gave them a very good orbital overlap. Iodine is huge, right? What kind of overlap is that? Doesn't seem very good, does it? So what is it with the halides? Well, when we look at the reactivity of the halide, right? So if I take a benzene and I say that benzene reacts at a rate of 1, right? Let's add something else. Let's say that there was a carbon chain. Again, the weakest activator, right? The weakest activator in the sense that it's only inductively donating. Let's give it like a 1.5, just for fun, right? Where would the halide rank here? Well, all 4 halides, F, Cl, Br, and I, when we do the reactions, turns out that they will always react slightly slower. Slightly slower. Okay. So in terms of activation, deactivation, it looks like they are deactivators, right? They reduce the electron density in the ring, right? They must be inductively pulling. Okay, that's easy to remember. So clearly they are deactivators. That must mean that they're meta-directing, right? Well, here's where things get a little interesting. If we look at the products, so if I look at, obviously this guy here, it's going to make an ortho and a pair product. So I'll put these dotted lines here to indicate that we get an ortho and pair product. Let me do it in a different color, right? We get ortho and a pair product, right? Again, if it's a deactivator, we might just expect it to be meta. But it turns out halogens give ortho and para products. So interesting. So halides are kind of a mixture of both. They're kind of in the middle. They are overall deactivating. So if I had to choose a category to put them in, they are deactivators, but they are also orthopara directors. Whoa, they are orthopara directors. Okay. So if I see a halide and I'm asked the question of, is it a deactivator? I say yes. But is it a meta-director? No, it's orthopara directing. Okay. So it's a little bit of deactivator, it's a little bit of activator. What's really important to take away from here is the fact that it's orthopara directing. right? Because when I go back here, remember there was one reaction we said won't work if it's a meta director, right? FC electrophiles will not be able to add into rings that are meta directing. Okay, so that's a bummer for these guys here. But hey, if I have an iodide, a bromide, or a chloride or a fluoride, hey, FC is totally fine with that. Because again, if you're orthopara directing, you will accept the Friedel-Crafts electrophile. So I can do the reaction where F adds in an electrophile that's Friedel-Crafts. So let's do this one here. Yeah, I can go ahead and add that. I can go ahead and add that. Although again, right, consider that this might be minor. This would be major because of that butyl effect. Right, but anyways, I can totally do that. Right. But if I were to compare it to the rate of, let's say, a toluene doing the same reaction, we have the same type of distribution possibly. We have the same type of products forming. Right, so again, we will still have the same major minor scenario. We have the same type of orthopara products, but this will be faster. This will just be slower, right? Because this is overall deactivating in terms of the electron density. Their reacts slightly slower, just slightly slower. Okay. I realized I forgot to mention this, right? This is actually why Friedel-Crafts alkylations are so bad at stopping at 1. Because if you take a benzene and you alkylate it, let's say with CH3, right? The reason why it polyalkylates is, hey, look, we just added an activator, right? So look at that. That's why we had that problem earlier, that we would get polyalkylations. I realized I forgot to mention that in the first section. I just mentioned that now. Okay. I'm not sure what Dr. Levens will want on this. Again, that was something I kind of posed as like, you should, if on your quiz you're asked from a naked benzene to do an alkylation, right? I would at the very least, I mean, if it's like something not very bulky, like a CH3Cl, right? I would, and then whatever metal you want to put, you can put there. I would at the very least put the monosub and the disub that's para. If it's something non-bulky, then you can probably also add in the disub ortho, right? I don't know if you'd want to add the trisub, like where there's like a chlorine, sorry, a carbon here. You possibly could. That's going to depend on what you've seen in lecture. I think very safe is just adding the monosub and a disub that's para. But at least you're showing them that you understood there should be some kind of over alkylation. If it's something a little bit bulkier though, like let's say an isopropyl, then I would only do the monosub and the disub, right? This one I would do, like if it's CH3, I would do all 3. Let me just make that clear. I would do all 3 if it were something not as bulky like a CH3. If it's like an isopropyl or even a tert-butyl, I'm only really drawing these 2. Again, just to show that you're thinking about that overactivation. Unless she told you in lecture, hey, only draw the monosub. Which in that case, I mean that's up to her. Okay. Cool. All right. Well, with that is the directing effects section, right? Whether I have an activator that gives electrons to the ring, makes it more nucleophilic, and adds things orthopara, right? Faster reactions. I can also have deactivators that kind of do the opposite. Take away electrons, make reactions slower, right? And they add things only meta. Just keep in mind the FC electrophile thing, right? This could be a good trivia question. Maybe not predictive products, but very good trivia question, right? Will something, what does FC not like to add to? Meta directing rings. Remember, it's not deactivated rings, it's meta directing rings, because we do have a type of deactivator, the halide, right? Overall deactivating, but it does do orthopara addition. So you can add in Friedel-Crafts electrophiles, right? It's just activating enough for that to be the case. Okay. Now, really, to set these rules in stone, the best thing you could possibly do is just do a lot of practice, right? Go out there and look at all the reactions you can possibly do. I mean, really, that's the best way to get better at these. Like, I mean, maybe you might see something like this and you're like, oh my God, what in the world is going on? right? Oh, well, look, I see a nitrogen with a lone pair next to the ring. It's okay that there's a ketone here because I mean, I've seen a ketone before as deactivating, but it's not next to the ring. Who cares, right? That's going to be an activator group. So I expect two products here, right? Although actually in real life, I'll tell you what, this reaction has a very big bias for the para position. Because that ketone, again, it kind of plays goalie. It kind of defends the ortho positions, right? It white knights those positions. On the other hand, let's, if we can write the flip of this, right, where I have a ketone connected to the ring, but I have the amine on the other side, right? Again, I do that same reaction. And I expect it to always go meta. And because I'm using my logic, right? I'm using my logic of what's connected to the ring. Remember, directing effects are always dictated by the adjacent position, right? The atom adjacent to the ring. That is what's going to dictate it. Don't care about all the other mumbo jumbo that might be on your ring, right? Focus on that first position. Does it have a lone pair? Is it a carbon chain? Ortho-para directing? Or is it cationic? Does it have a pi bond, right? Withdrawing is what I would guess there. Okay, cool. So with that, I'll leave you guys with one last example before we move on to the last part of this. I like to call this the Davis benzene because it kind of looks like a bike. Okay, but I have the Davis benzene, and I want to brominate this Davis benzene. Or actually, we've been doing so many brominations. Let's do it again. Actually, it's the easiest thing to draw. Okay, so the Davis benzene. So go ahead, pause, take a second, think about it, try to solve this. I know that there is two rings on here. That's kind of the point. Okay. So hopefully you paused and you thought for a little bit. You consider what the answer could be here. Again, this is just a classical look at each ring and look at what is next to it and consider what effects are going to be made by that thing next to it, right? If I look at the ring A here, I have a direct connection to a carbonyl, right? Hey, carbonyl, that's a deactivating group. So this is going to be a deactivated ring. If this reacts first, right, it's a carbonyl, so I expect it to go meta, right? No lone pairs, expect to go meta. On the other hand, look at this. This ring has a lone pair next to it, right? That is going to be, so we call this the B ring, right? That is going to be an activator group. And if this goes, right, it's going to be ortho-para. So what does it mean to be deactivated versus activated? Deactivator loses electrons, so we lower our electron, our electron excess, right? We are going to be less nucleophilic. Our reaction is going to be slower. So I'm not betting my kidney that this one's the one that reacts first, right? Especially when we have an activator, which we know gives electrons to the ring, makes it more juiced up, makes it more willing to react, right? A lot more hyper this ring. This is going to be the more nucleophilic ring that attacks first. Okay, and again, it's ortho-para directing. So I'm going to just annotate here. I'm going to put pH. pH just means a benzene ring. But we're going to have a bromine here. Usually, I mean, this is probably the major product. We're also going to have a product where the bromine is here, right? Again, but this is the major product. Okay, cool. So look at that. That was a kind of tough example, but using what we knew about ortho-para direction, and we focused on one ring at a time, it actually wasn't that bad. It's actually pretty simple. Okay, cool. All right. So in terms of concepts, we'll call it there on the one additions, or sorry, I guess the two additions. I think we're fairly good on that now. Got all that settled. So let's consider one last thing. And actually, I really check your notes because I think this might be more of 118 thing. Maybe we can even call this video short because maybe this is not something that needs to be covered. But if we add in one thing and we get a directing effect based on that one thing, right? So we get like an E here, and then we get a directing effect, right? Because let's say it's a meta director, we can get E here. Let's just say this is meta, right? Here. So we added E1, now we added 2. What happens if I add another electrophile? Oof. So I can add 2 electrophiles at the same time, or 2 electrophiles in the same reaction, right? What's going to go on there, right? What's going to happen if this is ortho-para, this is ortho-para, or maybe they're both meta, or maybe one's meta, one's ortho-para? What are we going to do, right? This could be quite the conundrum. So let's go. I'm going to go through some key examples. We'll call it, I'll give it 15 more minutes, and then we'll end it because I don't want this to be more than the hour and 15 that I was. I didn't want to be more than an hour. I think it might have hit the hour mark by now. But anyways, let's just go through this really quickly. Let's do this here. HNO3. So we get NO2 here, and then we'll do Br2, FeBr3. Okay, so we get a Br here. Oops, sorry, no, let's keep NO2 there. And we'll put Br here. So they're meta. Okay. What happens if I add in, let's say, what happens if I add in, I'll just do Cl2, whatever, screw it. It's the easiest thing to add in, honestly. Cl2, FeCl3. Where does the chlorine go? So there is a couple guidelines we can follow. And usually you can follow it in a hierarchy. So we'll talk about the most important, the second important, the third important. That should help you out with all of these. Okay. But the first thing you should always look for is an orthopair director, because the first rule is going to be that if there's any orthopair director, regardless of its strength, orthopara will always beat meta in direction. That shouldn't be surprising. We just saw that on the other page, didn't we? We said that if we had a ring that was orthopara directing and a ring that was meta directing, the orthopara was the one that won, right? Activated always beats deactivated. So activators will always be more important than deactivators. Okay. So on these two, right? I mean, I could just do a very quick analysis of, hey, who has a lone pair, or who, is there a carbon chain, and is there anything that's, cationic, right? Here I just kind of chose the most iconic of the two, right? NO2 and Br. Those are things that I can add very easily. And yeah, Br is going to be our director. So if this electrophile adds in any position, right, Br is directing the electronics on this, right? It's giving electrons, right? It's allowing for the intermediates, it's allowing for the electrophiles to add orthopara. So that's what we're going to do here. So we can add either here or we can add here, right? In the case of the bromine, or sorry, in the case of this chlorine, right? We will just get these two products here. Okay. Now, whether one or the other is better, it is not very clear in this one, because we have two things next to each other and one thing, two things next to each other and one thing. It depends on whether NO2 wants to be next to something or not. Not that big of a deal. Again, if we have orthopaired direction, usually the answer is going to be both of them. But in this case, if we draw out the product, we can see that there's no clear winner, right? They're both about the same. So that's where that chlorine is going to go. Okay. So we just have to look for the orthopair director and see where it takes us. Right? In this case, it takes us clearly to these two products, or maybe not that clearly, right? It's like a toss-up. We don't know which one's better. Another example of this is if I just reverse the order of addition, right? So again, just going to annotate here just for the sake of time. Oops. And let's add an HNO3 here. Okay. In this case, we'll get an NO2 here, and we'll get an NO2 here. So this is where this gets a little exciting, because now we have two different examples we can look at. And again, we're going to ask that question of, if I add chlorine, where is it going to go? Again, for this one, orthopara wins, right? So Br directs. And if I look at the one on the right, this one's a bit simpler, right? I can direct ortho, para, right, to those positions there. I guess I should have marked it here. We can direct here. Oh, actually, I missed one on this one. I realized I missed one. So I'm going to go ahead and draw it here. And maybe after we talk about this bottom one, you'll see why I unconsciously didn't even consider this one here. Okay. Maybe you guys can start to think about why I didn't even consider, why I didn't even bat an eye to talk about this one. Okay. But we'll come back to this one. Okay. But here, right, we have ortho, para, and para, right? Para director, or the para direction is blocked because there's already something there. But these two positions here are essentially identical, right? They both make the same product. So at the very least, one of the products here is just going to be this here, which is functionally identical to this one up here. All right, let me put this over here. I don't want you guys to think that they're all in the same mixture. These are different problems. So these two are the same, right? So we made the same product in those. What about this one, right? When I look at my ortho and para, again, I do have that same thing where I have an NO2 already in the ortho position, so I kind of get rid of it. I don't have to worry about something going there. But I get a bromine here, NO2 here, and a chlorine here versus this here. Now here, I do think that there is a big difference. I think that one of these products is way more likely to form than the other one, right? Maybe consider something I mentioned earlier about how there's a certain effect that is super hyper important in these rings because of the planarity of it. Okay. I like to call this, when I explain this, when I'm tutoring students, like to have like a fun way to remember it. I call this the BART dilemma or the subway dilemma, whatever train system you use or have wherever you grew up, right? This is that train dilemma. You enter a train, right? You enter the BART. You have to sit down somewhere, right? And there's only 2 open seats. Okay. You can sit across from this bromide, or you can sit right next to the bromide, where you might even also catch the bromide, the NO2 passing kisses and being cute with each other and doing things that you don't want, you don't want to be a part of. Right. So either you are the neighbor to these guys or sitting next to them throughout the whole your BART ride, or you sit as far away as possible from them. I mean, come on, guys. What are we always choosing here? I know what I'm always choosing, right? I'm always choosing to I might not even enter the BART, but I'm always choosing to go as far away from each other. And it's the same logic with these rings, okay? Steric effects are huge in benzene rings. Again, they're planar. They're always going to be steric, right, if there's 2 things next to each other. So we are never going to observe anything that forms 3 things next to each other, okay? Another rule of thumb you can use here that I like to use, 3 is a crowd. 3 is a crowd. That's not a hard thing to remember. 3 is a crowd. So if you ever draw 3 things next to each other, that's probably wrong. Okay, this is never, ever, ever going to form. Okay, and that's why here I unconsciously didn't even consider this because my eye glazed over it. It kind of shut down to that possibility of ever happening. Okay, so 3 things next to each other. Yuck. We don't want that. It's not going to happen. Okay, way too much steric effect. But 2 things next to each other is totally fine. That's not too bad. I mean, again, these 2 were equal in level. And I meant up here. These 2 were equal in level, right? They both have 2 things next to each other, so you couldn't really tell a difference between them in terms of sterics, but you could tell between this one and this one, right? This one for sure is going to form over this one because it's way too steric. Okay, cool. So whenever you have 2 directors on a ring and it's an orthopara versus a meta, orthopara always wins, meta will always lose. In the case that you have 2 orthopara directors, let's say that I have NO2. I'm just going to quickly annotate these just to get them out. NH2. I'm going to do a special move here because I realize now that you're probably never going to get asked this question. I don't think you guys ever talked about this, and I forgot to talk about this. But if you try to do a Friedel-Crafts on a free aniline, so an NH2 aniline, again, if this is on your notes, by all means, please erase it from your brain. But actually, the first thing that happens is the aniline attacks the acyl chloride instead of the benzene doing it. You're actually going to learn this reaction in the next section in carbonyl. So it makes more sense when we talk about carbonyls first. The general idea behind this is that if you have an oxygen or a nitrogen, so in this case aniline, or if we had phenol, the nitrogen atom is a better nucleophile than the benzene ring, right? The benzene ring is stable; it doesn't want to react, but nitrogen can. So things like Friedel-Crafts, alkylations, or acylations are actually also not too great on NH2s and OHs. So in both of these cases, let's say that I had an OH here. This also kind of sucks because we have a better nucleophile on the N and the O. So these guys usually add that group first. Okay. If you want to do a Friedel-Crafts after this, you totally can, right? The direction effect is also still there, right? Because these guys still have lone pairs next to the ring. So you can still have the same directing effect. I can do the same Friedel-Crafts again. You just have to do it in 2 steps. There's actually a modification of this known as the Fries rearrangement that kind of gets rid of this. I believe you do it in UV. But what it does is it actually, when you get to here, it actually rearrange to give you your Friedel-Crafts product. So this is advanced chemistry. This is like 128, or no, not even 128. This is like 231 level. This reaction here known as the hEArS rearrangement. Pretty sure you just use UV, and it will just shift it over. Pretty cool reaction, that one. But anyways, I'm just kind of building here just to get to a point, and just including that just in case you mentioned that in lecture. If that was not mentioned in lecture, you're not responsible for that. Okay, but you can go ahead and add the acyl group, and then again, let's go ahead and add in like a Br2 here. Or wait, sorry, no, I did that because I wanted to add the acyl group. Sorry. Now I remember why I did that. And then let's just consider this at the para position. Okay. I can hydrogenate that ketone. That'll give me the R group here. So all of that just to just to do this. Right, just to get to this point here where I can potentially build up to 2 orthopara directors on the same ring. Oh, you know what? I'm so stupid. You could have done all of this too. Sorry, I apologize if anyone wrote that. You could just do Br2 here. Forgot my favorite reaction. Okay, my bad. Anyways, Br right there, boom. Now we have 2 orthopara directors, and the question becomes, where does the next electrophile go, right? If we have 2 orthopara. So the rule here is if there's 2 orthopara, the strong orthopara beats the weak orthopara, right? Obviously, we don't want to give off the message that the strong are better than the weak, but it just happens so to be the case here. Right, it should make sense too, because technically halides are deactivating groups, right? They're the bare minimum orthopara directors, right? They're still deactivator groups. But if you have 2 orthopara groups, the stronger one wins. That's the person that we want to pay attention to as to where something go. So we're gonna get, let's say, the next electrophile at these 3 positions here, right? Again, of these 2 positions, right? You could draw out the 3 products. You can kind of see what's gonna happen though. Right, we either get this situation, just random electrophile, who cares what it is, right? Or we get this here, right? Obviously, this never forms. It's always going to be the one on the left. Okay, so this is the guy that's going to form. No doubt about it. I'm not stressed about that. Same thing if I had, like, let's say an OR group and potentially like a carbon group, let's say meta here, right? Again, between these 2, oxygen is it's a better donating group, stronger donating group. So that's the guy who directs. We have these 3 positions here. Hopefully you can tell me which position without a shadow of a doubt which one it's going to go to, or which one it's not going to go to, sorry. Definitely not going here. 3 is a crowd. So it'll go either here or here. It'll depend on which position is more steric, because if we were to draw out just the substitution patterns, right, you can't really tell a difference between these 2 in terms of sterics. At least we won't expect you guys to know that difference. So that's there. Okay, cool. So just to wrap this up, sorry, I know I'm speeding through this a little bit, but let's go through the very last thing to know, right, is if there's a meta director, right, you want the weakest meta director will beat the strongest meta director. Okay, actually, let me write this a little bit better. A weak meta director will direct over a strong meta director. That should also make sense. I know it feels a little unintuitive at first, but that should make sense. Deactivators pull out electrons. So if the whole point of the benzene is that it wants electrons to do reactions, the guy that pulls it out the least is the one that's going to be the director of the reaction. Okay, so I'll just quickly, let's just do it from here, right? NO2, I mentioned, just know that's the most powerful one. So anything in its face is weak. So the guy who wins direction is going to be this carbonyl here. We can either direct here or here based on that. Again, hopefully you guys can see where it is always going to go. electrophile will always go here because that other position is blank as a crowd, right? If we put it here, 3 is a crowd. That's definitely not going to happen. So the electrophile is going to go there. If I do this from the meta perspective, hopefully you can see that it doesn't matter who you pay attention to. This is sort of a foolproof method, because if I pay attention to this NO2, it goes here or here, but that position's already taken. And if I pay attention to this meta group, it goes here or it goes here, right? So again, they both kind of direct to the same position, right? Two meta directors that are meta will always direct to that third meta position. Okay, so this is the only product that you see. Okay, cool. So you can actually even possibly, I know maybe I'm stretching into a bit of time here, so I apologize, but you could even take this as far as saying you could have a 3 sub ring like this, and very, very easily you could guess. Wait, can you guess on this? Okay, maybe not very easily, but you could make a very good. Oh, I see what I did wrong. What I wanted to do was this. There we go. You could take even a tri-sub ring like this one. No, not this one. Is it this? Is that going to fix it? Is that what I wanted to do? No. What am I doing wrong? Shoot, I had an example. Oh, yeah, this here. I thought I had that before, didn't I? Did I have that before? Or did I just have this in the wrong position? Was that? Yeah, that was the problem. I see. I had this in the wrong position. So you can take something like this with 3 groups on it. You know, something that looks like it'll give you a terrible time. But again, all you have to look for is go through those three criteria, right? Orthopara beats meta. Strong orthopara beats weak orthopara, or weak meta beats strong meta, whatever. And use that to guide you. I mean, we have a lone pair donator versus withdrawers here, so the lone pair donator wins. I have 2 possible positions. I can add things, right? Technically 3, but something's already there. And again, just ask yourself, when I draw out these patterns, where should things go? Right? Do I want something here? And now it's not even 4 as a crowd. It's 4. Sorry, it's not even 3. It's 4 as a crowd. If something goes here, that's terrible. That's the biggest crowd we've ever seen. Don't want that. Or I can split this up into 2 crowds, which I think that's not too bad, right? That's just having like a partner right next to you, right? That's not a big deal. Okay, cool. So again, I mean, this is definitely like 128 level, but you can see that even an 8 student can dissect this just by knowing these simple rules. Okay, cool. I realize there's actually one last example I could go over. So I will go over it really quickly. This one here, both of these, I mean, this is just a very exception problem. If I were to add an electrophile, technically, you know, it should go here, the electrophile, but we did just talk about how, I mean, again, things next to the turbil are really bad. So we want to put it next to the chlorine. This is the one time that this can happen, despite the fact that this is going to be our activator, right? So yeah, cool. All right. Well, with that, I'm going to go ahead and call it. Hopefully this helps you guys out. Again, mainly going over the concepts. I suspect maybe the last 15 minutes might not even be necessary, because maybe you guys didn't go over it, but we'll see. Anything I missed or might have messed up, let me know. If you have any questions, please ask. I mean, whenever hopefully your quiz is like on Wednesday. It might be on Monday though. It makes sense if it's on Monday. But anyways, if it is on either day, just remember, just ask questions. Prepare yourselves, and again, work on managing your reactions. Right? It's no longer just memorizing everything. You got to learn the patterns. If you don't, you're going to find yourself drowning before every single quiz trying to memorize everything. I don't want you guys to do that. Okay, cool. All right, I'm going to call it here. You guys have a good one. Good night.